Okay, so again, I just want to mention we're covering this computational stuff, computer modeling, computer simulation. Absolutely, I guarantee you, of all this stuff, I mean, I have the impression you folks have absorbed a decent amount of this. Last semester, really wasn't too sure. This semester, I feel like you folks have gotten down a really good amount. I hope. Just my impression. But I'm telling you, what I'm showing you how today, this could last a lifetime. The stuff I'm showing you, I am still using it. Obviously, there's a disconnect between what you learn in the class and what you actually do. So you engineers, right? You probably learn about strain and stress. But are you now ready tomorrow to build the space shuttle? Are you ready to say, well, the flange has to be 3 inches thick or the space shuttle blows up? Right? There's a bit of a disconnect between learning and doing. This bridges that disconnect. So this is how you do. All right? So I think this is something that you'll find valuable. It's really fun. And you can apply this in your research. One example was I had a project where we had a quantum dot and we had a charged molecule on its surface. So what I wanted to do was model how the electrostatic potential inside the quantum dot changed due to this charged species on the surface. So basically, what's the electric field of this charged species? This is how I did it. It was an integral part of our paper. So there you go. All right, so one is called, the method we're covering today, which won't take too much longer to finish. And good thing I have a backup pen, so it's my last backup pen. All right, so remember the finite difference method, you will generally hear it called FDM. And then we're also going to cover split operator. The split operator method, which has, it's pretty cool too. This finite difference, this is stupid simple. In just a few lines of code, you can solve some really complex things. But it's basically one-dimensional. That's one problem. Now, there's lots of one-dimensional problems, including purely radial Hamiltonians for like particle in a sphere. Now, technically, the angles in a lot of spherical problems, the angles really just almost never do anything. Everything's in a ground 1s state, so there's no angle dependence. So you can do three-dimensional calculations with finite difference, assuming you're in spherical coordinates and the angles don't matter, which is true of so many things. So you actually really can do 3D. But remember, if you're doing radial coordinates and spherical coordinates, it's really one-dimensional. Split operator can do multi-dimensional, including 3D. It's more versatile in that regard, but harder to program. So heads up, that's the big deal. Okay, so we're covering number 1. Now recall last time I pointed out to you that in MATLAB, for example, you have discrete data sets, right? So you've created a particle in a box wave function. It has 5 points. Now you know that that this goes from like 0 to 1 nanometer. So therefore, each point is 0.2 nanometers. You know that. MATLAB doesn't. MATLAB just says 0.1, 2, 3, 4, 5. So be careful of that. You can kind of work with either representation, what I'm about to show you. Maybe we'll do an example. Okay. Now the trick to this, of course, is you've got to do a derivative, and then you've got to do another derivative. Because that's a double derivative, and now you've basically got the Hamiltonian. Now you've got a way to turn a finite data set of numbers and take a double derivative. If you can do that, you basically have an operator. So again, the ability to take the double derivative is akin to having the Hamiltonian operator. So we just got to figure out how to take a derivative and then again just do the same thing twice. Or we can do something a little fancier, and I can start solving the Schrodinger equation with that data set. But now here's where it gets even funny, though. Actually, if you have the Hamiltonian, you don't need to write a wave function. This thing will do it for you, right? All you have to do is say, hey, what are the eigenvalues and the eigenvectors of the Hamiltonian? So notice that I'm going to try to calculate the Hamiltonian of this wave function. But reality is, once I have the Hamiltonian itself, I don't even need this, right? I just go into MATLAB and say, hey, what's the eigenvalue of that Hamiltonian? Hey, what's the eigenvector of that Hamiltonian? So anyway, again, you've done some of this, but let me just start doing things. Okay. Now, last time we talked about how we started talking practically about how to calculate a single derivative. And of course, the derivative is the slope of the data, and that requires two data points. You're going to lose a data point in the process. But what we talked about was, if you want to begin your algorithm at the first data point, that's fine, in which case you lose the last data point. You can begin at the second data point and then keep the first data point. Anyways, look, the point is if you start here, you have two possible points with which to calculate the slope. Okay, so the way I'm going to represent that is to say I'm going to have a function which gives me the derivative. And so that will be a result of the point behind the current one, the point at where I'm talking about, so that's the second point, excuse me, and the point ahead. All right, so again, if I'm going to calculate the derivative of this wave function at this point, I'm going to want to know what the value of that point is, the one ahead of me and the one behind me. So I'm going to basically like calculate the derivative and then like average it together. So just like one of you suggested. Okay. Now this is called a 3-point stencil. So, sorry, stencil. Okay. You sometimes will hear this. You'll hear about stencils every now and then. So now you know what it is. 3 points, 1, 2, 3. Now on your homework, guess what? You're going to do. You're going to do what I'm about to do for 5 points. But guess what? I'll show you how to get MATLAB. I'm going to do a derivation, but I'll show you how to get MATLAB to do it for you. Anyway, so okay, this next part is funky. What I want to do is what are the optimal A, B, and C. So it has to be accurate. But again, we talked about how there's a couple of ways to do this. We can make C 0 and only consider the point behind us. We can make A 0 and only consider this point. So the idea being is that we have some play with A, B, and C. So what can we do to figure out the best A, B, and C to give us the most accurate slope? And obviously, I'm not going to set either A or C 0 because it sounds like the average of the two slopes, calculating the slope behind me and slope in front of me, and averaging that result would be the best you could possibly do. Okay, all right, now here's how you do it. Now again, this is going to sound like it makes sense at first, and then that's great, but don't stare at it too much because then it gets confusing, in all honesty. All right, so we're going to use a Taylor series. Now we're going to do a Taylor series for f of x minus h, f of x plus h. All right, so that's step 1. Then collect the f prime of x, that's step 2. Okay, now you know a Taylor series looks like this. And I'm going to have to use some dashes. Sakurai, I just love those dashes. And we're going to be about point A. I'm using a dash because I'll use the letter x for the data, and I'm using an x dash for the derivation because they won't quite be the same thing. Okay, so I am again showing you the definition of a Taylor series, and I'm going to stop at the double derivative. So this is the series about point A. So you Wikipedia Taylor series and says, okay, for a function, here's the Taylor series, and if you want to make it most accurate at point A, which isn't necessarily 0, this is how you do it. Okay. Now, one thing to note is, you notice how I stopped at the second derivative? 1, 2, 3, ABC. I'm looking for ABC. Those are 3 unknowns. 1, 2, 3 terms. Remember, to solve a system of equations for 3 unknowns, you need at least 3 equations. Okay, excuse me. Maybe I am getting cold. Yeah. Anyway, sorry about that. Okay, now I've got to remind myself. Okay, this is where okay, not weird. Taylor series, you saw it in high school. This is where it gets a little funky, so maybe try not to, seriously, try not to overthink it. Okay. Okay, we're going to start with f of x plus h. Okay. Oh, excuse me. Yeah. Okay. X plus h is equal to x prime in my formula. X, the function x, is a. Okay, so again, a will be x, meaning, where am I at on my x-axis? So just like you know it will substitute in a, and of course then I need to substitute in for x prime, and that's our x plus h. And notice that kind of lines up. Again, in all honesty, if you stare at this and stare at this, it makes less and less sense, so maybe just don't stare at it too much. I'm just using the formula, but I am kind of using it in a weird way. But let's not blow our minds too much on this, all right? Okay, so f of x plus h. Now remember, h is like 1, h is 1, right? So it means if we're at point 2, then, x plus h is 0.3 and x minus h is 0.1. All right, so now the reason that we use the letter h is that it depends on how you're thinking about it. It's 1 if you're talking about the data point, or it could be 0.2 nanometers if you want to think of it like in its what it represents. So it can be both. So that's why we use a letter h instead of saying just like plus or minus 1. Okay, so what is this? Okay, so this is, we go here, so f of a, and a is now x. Okay, now I've got x plus h, because that's x prime, minus a, but a is x. F prime of a, but, derivative, but a is derivative at point a, but a is x. Again, I tell you, it gets a little funky. Same thing, x plus h, that's x prime, a is x. Double derivative at point A, which is actually x. And again, we're going to leave off higher order terms. Okay. F of x plus h f prime of x plus h squared f double prime x double derivative, and again we'll stop there. Okay, now if you do this for f of x minus h, you're going to get, guess what, the same thing. F of x, you're going to get minus h. So you're obviously fully capable of doing the incredibly minor algebra to figure out what I've done right now. Sorry, we'll do 2. Okay. big surprise here. Positive, positive, everything's positive, positive, negative, positive on odd powers of your Taylor series. So now, then again, easiest of all is just f of x itself, which is just equal to f of x. Obviously, by definition, there can't be any more terms. F of x is equal to f of x. Okay, now again, remind you what I've done. I've got these, right? F of x is just f of x. X plus h is this function here. And x minus h is this thing here. And again, I stopped at the second derivative for reasons that will be apparent in a moment. And now what I do is I've not used the board too well again. And so let me now put them together, but let me put this a, b, and c in there. So I'm going to just rewrite the same thing. Let's see here. Okay, so f prime a times blah, blah, blah. Okay, so this is a times f of x minus h. So that is a times f of x minus ah. Now the prime of x, the first derivative, plus ah squared to the double prime of x. We're going to stop there. Okay, so that's this one. Okay, let's do, okay, so that's this term. There's nothing more to do. Now I'll add in x plus h. Okay, this is t plus c, h f prime of x plus c h squared over 2. Okay. Now, last step. Actually, this is kind of it. So here's the cool thing. F prime of x is equal to all this, right? Here, let me, right? Yeah, we're all okay? Well, there's a problem. How can the derivative of a function be equal to its function? How can the derivative of a function be equal to its double derivative? Huh? No, that's nonsense. There's an easy solution. What if a plus b plus c equal to, guess what? Right. Let's get rid of it. Yeah, real easy. Ah squared plus ch squared 2 over 2 equal to 0. Okay. But then we have to make the single derivative that better actually that better be 1, right? Minus a. So I was looking for. I got a little confused there because I was like, oh, excuse me. I was looking at it. I was like, wait, I got to have 3 equations, right? A, B, C are my unknowns. Those are 3 unknowns. I better have 3 equations, right? So this kills off the function, that kills off the double derivative, and that means that the single derivative is equal to the single derivative, which it better well be. Okay, now what do we get out of this? Okay, the 2's cancel, the h, so a is equal to minus c. From right there, that's pretty obvious. Okay, if a is equal to minus c, then what do we got here? A is equal to minus c, and then we got b is equal to 0. And then we got c is what? That's 2ch is 1.
There we go. So C is 1 over 2h, A is minus 1 over 2h, and B is 0. Now h also could be, if you want to use the representation of data points, h is 1. So what do you got? The derivative of a function is 1/2 the function 1 point away minus 1/2 the function minus 1 point away. There you go. Now, reality is that's the same thing. Remember how we were saying let's calculate the two slopes and average them together? That's actually the same thing. Just you'd have to do some algebra. You'd have to do 1 or 2 steps of algebra. But that's what this comes down to. So take the point ahead times half, subtract the point behind you times half. That is the best calculation of the slope you could possibly make. Ta-da! Notice that I've already got the equations here. Let's do the double derivative. Now, you could just do what I just wrote twice. Just do this twice to the data set. That would be the double derivative. But, you know, I don't know that it would be the best formula for the double derivative. And look at this. I've got, okay, ABC is still 0 for the double derivative. A minus CH minus CH would be 0. And AH squared over 2 plus CH squared over 2 would be equal to 1. Right? So let's see here. So for the double derivative, which actually would be more useful for a Hamiltonian, what you've got is a system of equations of A plus B plus C equals to 0. A minus A plus C is equal to 0. I just did some, I just divided out by H. That's this minus AH plus CH is equal to 0. So I just divided out the H. And then it gets a little bit more complicated. I got A plus C is equal to 1, and I'm going to multiply that by 2. 2 times 1 is 2 over H squared. Okay, so let's see. So therefore, A is equal to C. Therefore, 2C is equal to, therefore C is 1 over H squared. And therefore, A is 1 over H squared. And then B is equal to what? Minus 2 over H squared. Yeah. Okay, so now the derivative, double derivative at x is f of the point behind minus 2 times the point in the middle that you're talking about plus the point ahead. Kind of neat, right? Now, again, that you would average the slope of the point in front of you and the point behind you to get the best value for the derivative is probably intuitive. Algebraically, it just turns into this. That doesn't particularly blow my mind. But that a double derivative at a point, it's just a point ahead of you, the point behind you minus 2, your current value. That's the best double derivative you could get. I don't know. There it is. Not that hard. I've tried. It actually really does work. It works really quite well. Okay, so note that with this, now I use a representation of H being the data point. You really can't do that. That's not a good idea. So let's go back to the representation of H being a discrete value like 0.2 nanometers in that example I gave. So let's not think of H as what data point we're at. Let's think of it as a finite step in our simulation, which of course is a parameter you might set. So you can imagine if you're trying to solve for the particle in a box problem, what you do is you might want to have a 1 nanometer box. You might want to have 1 or 200 points. So there you go. So every point is 0.01 nanometer. Okay, the way this works is, and let me just do the Schrödinger equation. Minus h bar squared over 2m, and let's do an electron times, okay, so, all right, in matrix form, p squared over 2m is minus h bar squared over 2m, double derivative, and this is the double derivative in matrix form. Again, on a finite data set. Okay, this is going to start out looking a little weird. Just hold on for 1 second. Minus 2, 1, 0, 0. I'm going to stop there. Now that looks weird, right? Now here's where it looks more correct. And I'll explain why it looks a little weird, and then now you're going to see that again in this last one. Okay, now you operate on the wave function, which will only be 4 points. Now again, I can't dramatically emphasize enough. You need to work with at least 100 data points, maybe more like 1,000. You know, the computer isn't going to particularly go bonkers on you if you give it a whole bunch of numbers to work with. It just goes a little slower. Okay, so notice there's a little funkiness to this. 1 minus 2, 1, right? So we're doing the double derivative. 1 minus 2, 1. 1 minus 2, 1. 1 minus 2, 1. 1 minus 2. Okay. Notice that where's the 1 in front of it? Remember, when you calculate a double derivative, you have to sacrifice 2 points because you just do. There's no way to add the leading 1. Because if I do, I have to add a row. Right? So it's a chicken or egg problem. You're going to have to lose, the first data point is going to be screwed, and so is the last one. So when you calculate this for 4 points, you're going to come up with a semi-accurate double derivative for here and here for the first and last data points, and accurate double derivatives for the middle 2. Now, again, that's because that sounds awful. It's because I only have 4 data points. You really want 1,000. If you have 1,000, what you do is, when you get your results, just don't work with the first and last data point. Now, so you're going to lose a little bit there, but it's not a big deal, obviously. Okay. What else do I want to say? Okay, so notice that the Hamiltonian here is just p squared over 2m, which means it's a free wave. So, yeah, whatever. What can I say about this? So obviously the trick is that I hope all this makes sense. But what you can do is just create this matrix in MATLAB and say, what's the eigenvalues? Gives you that. What's the eigenvectors? Gives you that. But remember, you only need the Hamiltonian to know everything. You don't have to have some silly points for the starting wave function. You don't have to know the eigenvalues. Remember, it's going to solve the determinant of this minus the identity is equal to 0. Gives it enough to solve E. And once it has that, then it just goes back to this and solves for all the x1, x2, x3, x4. So it's kind of clever, right? Okay. Next thing is use atomic units, which you have learned. Therefore, minus h bar squared over 2me, because again, we're going to do all this with an electron, is equal to what? Minus 1? 1 half, that's right, minus a half. Now, 1 over h bar squared, h squared. So again, we're going to do a particle in a box. It's going to go from 1 to a nanometer. We're going to have 1,000 points. H is 1 over 1,000. Oh, I just screwed up. You have to work in Bohrs. Okay, so let's do a particle in a box. Now I have to stick with it, so I just kind of screwed up. 0, 1 nanometer. Now nanometer, that would be 18.9 bohrs. Yeah. I think so. Okay. Now if we have 1,000 points, H is 18.9 over 1,000. There you go. Ta-da! Seriously. Write an algorithm that creates this matrix. It's not particularly difficult. Yeah, the first one is a little bit of a pain, but you can come up with an algorithm that creates this relatively easy. Multiply every one of the elements by -0.5, and then multiply it by that, and then multiply it by that again, and then you're done. That's it. MATLAB then does everything else for you. Creates the eigenfunctions and the eigenvalues. So cool that, right? Okay. Next bit. This is for a free wave. We don't need free waves. We know what free wave. We know all about free waves. This is the last thing we really need to do, a half-assed numerical calculation of free waves. What you really want are harder things like ones with like something with potential, like a particle in a box, or maybe a sphere, a particle in a sphere. Particle in a sphere, that kind of sucked. Remember doing that? And you know, the whole 3D Hamiltonian bit. Let's do that with this stuff. Okay. Let's add in a potential. I'll tell you what. Actually, let's do hydrogen. Screw particle and sphere. Let's do hydrogen. We never actually solved hydrogen. Let's do H atom. Okay, the Hamiltonian is -0.5 del squared. Now that will come down to just a radial derivative, which we know is actually not 1 over r. It's not just the double derivative of r squared. Okay, again, in atomic units, we're down to this. Now remember, 1 over 4 pi e naught is also the number 1, which is unfreaking believably awesome. The thing to note is that when you create the Hamiltonian matrix, you say, hey, MATLAB, what are the eigenvalues? Those are in Hartrees. Go into Google, what's a Hartree to a kilojoule? It's this. There you go, you're done. Okay. Convert that to EVs, convert that to wave numbers. Okay. So, now, the way this is going to work, so this is the potential. Okay, the way this works is the Hamiltonian matrix is going to look like this. You're going to have -0.5 1 over h squared. Again, your grid spacing and terms. I won't even worry about it. We're going to do radial, so it's going to be a little bit more complicated. It's not terrible. Now, the way that the potential works, I'm sorry, we're going to do radial, right? So I should be using R. So, and I will continue to do at least 4 elements because you won't be left in a quandary. Okay. The potential energy part of these matrices, as much as, you know, we've gone through all the kinetic energy part, and again, I'll actually do the radial here in 1 second. It will be a little bit more complicated. The potential energy ends up being donkey simple. It's just a diagonal matrix. Now, so you could imagine, so a particle in a spherical trap. It would actually look something like this. It's a say that 1 nanometer. So we're going to have a particle in a 1 nanometer sphere. The potential energy goes to infinity at 1 nanometer. So now again, you can't plug in infinity to MATLAB, it won't accept it. So what you do is you would have the simulation go out to, say, we want to do this kind of far. I've done enough of these. You have to kind of play with this. Let's go up to 5 nanometers. Not a meter. Okay, and you would have this set to like a heart rate, which you should know is a bombastically large value of energy. That is an obscenely high number. So here's the trick. For our particle in the sphere calculation, which is what you're doing on your homework, to simulate a boundary at 1 nanometer or however large, you would just need to simulate a longer radial coordinate. It comes to the matrix comes to an end at some point. But so 0, 0, 0. Oh, we're at a nanometer. So then make that 1 to 5 nanometers until the end of your matrix, and it simulates this potential surface, which would be not perfectly a particle in a sphere because the boundary is not infinite. But again, a 1 Hartree barrier is gigantic for an electron. It's not going to penetrate. So anyway, that's how you handle potentials. It's not too difficult. There's one other thing you've got to know, which are boundary conditions. Boundary conditions on finite difference is actually the hidden thing that makes this hard that no one likes to talk about. When you find text online, so everything I just described, I figured out just by Googling, because I needed to use this a couple years ago. That's how I learned on Google. I got this far, and then I got stuck. Boundary conditions are terribly important, right? You're not going to find a description on how to do them properly. I had to figure it out from scratch. Because theoreticians never reveal everything. And unfortunately, when you're dealing with an equation, if you're missing a factor of 2, ain't nothing going to work. And they do this. So that's something to be aware of. Let me show you how they do it. Take spherical Bessel. Spherical Bessel functions, right? So I'm talking about a particle in a sphere. You know that they look like this, right? So the wave function of a particle in a sphere is a spherical Bessel function. We're going to do the S state. So the potential energy is what I described. There's no rotational component. L is 0. So we know that it needs to look like this. If you do the finite difference method, you're not going to get this for the wave function. It's going to converge to another solution, which is actually wrong. Remember that in quantum mechanics, the solution to the Hamiltonian, there can be multiple solutions to the Hamiltonian, multiple solutions to the double differential equation. In quantum, we reject the ones that are unphysical. That happens a lot. Remember that in quantum, you've only been shown in undergrad, you're only shown the solutions that make sense. You're not shown the solutions that don't make sense because you reject them. Okay, now to get the calculation to do this correctly, you have to incorporate boundary conditions. See, that's what's missing is boundary conditions, right? When I say that you reject nonsensical solutions, it means the nonsensical solutions violated a boundary condition. Or you may just have a boundary condition, just you may have a boundary condition. Okay, so let's say the wave function at x1 is equal to 1. Now let me go back to non-radial. Let me go back to Cartesian, or just x. Sorry about that. Okay. So what do you do to this? The trick here, right, so this one's kind of neat. That's how you do it. You're basically telling it that the fourth point is the number 1. That's the trick. Okay, that one's kind of silly. Here's one that's way more important. Say, here I'll do 3. Let's say this is your boundary condition. The slope has to be 0. Uh-oh. What do you do about that? I mean, we run into boundary conditions with slope. Slope has to be equal. Slope on the left is equal to slope on the right. Slope has got to be 0. Anyway, boundary conditions with smooth and continuous, the smooth part are slopes. Right? So how would you do that? Okay, now what this would mean is this. The wave function at point 4 minus the wave function at point 2, right, over 2h. Remember that what I've done is I've just used our 3-point stencil definition of the slope at the third point. Slope, not double derivative, right? So the slope at point 3 is the point ahead minus the point behind divided by 2. Okay? And what that means is point 4 is equal to point 2. That's all it means. It's flat, right? If the slope is 0, then the wave function is perfectly, what is this, horizontal, right? That means point are all in a line, a straight line, just exists. Okay, when you do that is, that's how you do it. See? Point 1 is 0, point 2 is 1, point 3 is 0, point 4 is 1. 2 and 4 are equal. There you go, slope is 0. That's how you do it. It's kind of neat, huh? Okay, last bit, oh God, I didn't finish this, is I mentioned I'm going to do radial. All right, so let's do radial. So I was doing Cartesian. I shouldn't have even brought this up. How are we going to do that? Okay, so the Hamiltonian kinetic energy, and for a particle, let's go back to particle in the sphere. It's right, that's awesome. That's with P states, D states, right? We've got particle in the sphere and has S, P, and D states. So of course we're going to do, let's not kill ourselves. Ground states matter the most for obvious reasons. For particle and sphere, it's an S state. So this term is gone. Okay, cool. All right, so what do you do? Now, the first thing to note is we talked about how to do derivatives, but what the hell do we do with this stuff? Okay, here's what you do. You convert it into not that this is just minus a half. You do a product rule expansion, and you should know that, again, it turns into this. The reason is this is way easier. I know what a derivative, double derivative is, and I know what a single derivative is. Okay, how it works is at the diagonal of your kinetic energy part of the Hamiltonian, it's minus h squared over 2me, whatever the step is. Now, if if there's a potential, if we are doing, say, hydrogen, it might be, you know, whatever, hydrogen or particle in a sphere, there's a term. Now remember, I'm doing the diagonal outlet. Now let's do diagonal plus 1. Okay, so this is, here, let me make it real clear. Okay, so I'm doing the -2s. Okay, now this one is going to be this point here, and again I'm doing a radial. So this is for x. This is for Cartesian, but now I'm doing radial. Okay, this is going to be my h bar squared over 2me, which is just -1/2. 1 over h squared, which again would just be the grid spacing. There you go. And the diagonal -1. So that would be here, here. So these are okay, so notice what you're seeing here. These first terms are actually the double derivative. That's this, right? So you can see the constants, so I'm assuming that. But look, you've got for a double derivative, right? It's like 1 minus 2, 1, right? 1, 1 minus 2, 1 minus 2, 1. Okay, now the single derivative has no amplitude at the center point for plus 1 minus minus 1. Plus minus 2 over r, right there. And again, we have to, yeah, there's your grid space. Okay, now remember that the value of r, which you see here, is determined by what line you're at. So 0.01 nanometer, which actually, sorry, it needs to be in Bohr's. So I'm kind of screwing that up. So again, depending on the length of your simulation, and again, convert these to Bohr. Sorry, I kind of blew that up a little bit, but so every line, you know if you're on the first row, second row, third row, that gives you the R, and that's what you plug into each one of these elements when you see the R. Anyway, I've gone over as usual. The code is not hard at all. You can certainly do a particle in a box. That's stupid easy. It's only just 4 or 5 lines of code. You can tell particle in a box. Particle in a sphere is a little bit more effort. But again, once you start actually programming this, you're going to laugh at how easy it is. Then you just say, MATLAB, give me eigenvalues. And that's it. It's done.